Hello and welcome to this today's lecture. So let's resume at the point where I had stopped last time. So I wrote down this small proposition which says that if you are given a non-zero n form, then that gives an orientation on V, and we have a statement saying when they give the same orientation. So now let's see what really we have to prove here. Well, so what I want to say is that this gives an orientation is that I want to say that this is, we want to show that this thing here is an equivalence class of tilde. In other words, by the way, this before I proceed, this the defining equation in terms of this matrix A, the change of basis matrix A. So let's write this, the shorthand notation for this set of equations. Let's write it as this B1 equals AB2. So the meaning of this is precisely this. So using that notation, so we want to show that this O omega is an equivalence class of tilde. So i.e. so first let's show that this omega is contained in an equivalence class. Contained in an equivalence class. So what does it mean to say it's contained in? If now the i.e. if B1 equals AB2 with determinant A positive, in another way of saying B1 equivalent to B2. So anything, so I've taken an two things, right, contained. So if B1 equals AB2 with this, well, instead of saying, in other words, so let me just start like this. Let B1 equals AB2 with determinant A positive. So let's see what this gives us. So this, let's calculate V1 up to Vn. As we have seen many times, in fact one can just use the definition of the determinant to see what I'm about to write down. So this will be, if I write down V1 etc. in terms of, so B1 is same notation as before. If I write down V1 in terms of the Wi's, then this will be the same as determinant of the matrix A, then, oops, this is not quite OV, this doesn't make sense. So what I want is omega. Omega of this is equal to omega of W1, Wn. So we have done this several times in the previous lecture. So therefore, and since det A is positive, omega V1 Vn and omega this have the same sign. So what does this tell us? And conversely as well, if these two have the same sign, then that A is positive. and if omega v1 have the same sign, then det A is positive. Also, I should have remarked that where have we used the hypothesis that omega is non-zero? Well, of course, here we are talking about sign, which doesn't make sense if it is 0. But what the hypothesis that omega is non-zero means that it's not the 0 form. So means that omega of x1 xn is not equal to 0 for some x1 xn in V, for some choice of vectors. But this immediately implies that if I write down these vectors in terms of any basis, then this thing here, well, the left hand side, since it's an n form, I'll just get, this will be a multiple of what it is for a basis vector. So implies that omega v1 vn is not equal to 0 for any basis v1 up to vn. So the assumption that the form is non-zero is just that it's not, there is some input choice of input vectors for which I don't get the 0 output, but that implies that if I plug in any basis vectors, it will be non-zero just by expanding this and using multilinearity and alternating properties of omega. Well, here, right, so this equation now shows that this to say that omega v1 v2 vn and omega w1 w2 wn have the same sign is the same thing as saying determinant A is greater than 0. Well, that proves what we want exactly. Actually, I don't need to say it's contained in and so on. At one go, we get it straight away. Simply because actually I am interested in the case that this when this sign is actually positive, but I am dealing with the, in particular, the set of all bases such that omega is an equivalence class. Because, well, if you have any two B's inside the set, B1 and B2 inside this particular set, then we have seen that the determinant is positive. So that means that this set is contained in an equivalence class. On the other hand, if there is something else in the equivalence class related to something in this set, again that new basis will have to have the same sign as omega, will also have to have positive omega. So that new basis will also have to belong to the set. So the set is exactly equal to the equivalence class. And it's clear that from the way it's defined that this condition holds, that positive constant. This is, after all, it's completely a tautology to say that the constant has to be positive to get the same equivalence class. write. So as an example, the standard orientation on Rn. So recall that this is the all bases B which are equivalent to this basis, standard basis written in an ordered manner. Set of all B which are equivalent to this is given by the form dx1 wedge dxn. Given by the n form dx1 wedge dxn. Here we have a so in other words, I just have to check that this particular form evaluated on even up to en is positive. And in fact, we know what it is exactly. It is this one forms are dual to these one forms. Therefore, I just get the value to be actually 1. And there's no permutation going on. It's 1 to n here, 1 to n here. And an earlier lemma tells us that this n form evaluated on even up to en is exactly 1, which is positive. That's all I need to know to say that this orientation is given by this form. Now let's move on to manifolds. So there are two ways one can, at least two ways one can think about an orientation. One is what we just discussed tells us that to have an orientation is the same thing as picking out a non-zero n form. Actually, it's not quite that, because of this constant C business. It is picking out not a single form, but rather a sort of half line of forms. So all multiples of some form, positive multiples of a given form, is the same thing as having a orientation. But at least one thing is true, that if I have a non-zero form on V, I'll certainly get an orientation. So what one can try to do is, we say that M is oriented if oriented or orientable is also another thing. Or when I say oriented, I already have a form in mind. M is oriented if there is an n form omega actually let me drop the p, omega n. So the dimension of the manifold is n, of course. There's an n form such that all I require is that at each point it's not the zero form. Omega p is not equal to the zero form, and a n t p m. And this is for all p in M. Nowhere should it be the zero form. this will do so as a definition, because on each tangent space I'll get an orientation which amounts to saying I'll be able to say when if you give me a basis of a tangent space at any point, I can say whether it's an oriented basis or not, because this omega gives rise to an orientation on each tangent space. Equivalently, here say that orientable as opposed to oriented, if there is an atlas, a collection of charts whose union is all of M, covering M, U alpha, phi alpha. There's an atlas such that the derivative of the transition functions, so whenever we have a transition function, so that will be phi phi beta composed with phi alpha inverse. This derivative, the transition functions will be diffeomorphisms between open sets in Rn, and the derivative will be linear isomorphisms between Rn and linear isomorphisms of Rn. And so I look at the determinant of that. This should be positive at every point in the domain of this transition function. So at every point in the domain of phi beta composed with phi alpha inverse. Now here this doesn't directly give me a specific orientation. That's why I call it orientable. However, I can use this to get an orientation on M. So that's why I say equivalently. And conversely, if M is oriented, I can get a system, an atlas of charts. So this is called, when we have such an atlas, I call it it's called an oriented atlas. So there are two ways of thinking about orientation. One is to talk about n forms. The other one is in terms of transition functions, rather the determinant of the derivatives of transition functions. And the two are equivalent. So let's quickly see why they are the same. Suppose we have a nowhere 0 n form omega n omega, the top degree n form. So I'm starting with this. Then let's see from this how we can get a oriented atlas. Well, let's draw our usual picture. So this is one is U alpha, U beta, or rather, let me just, instead of starting like this, I'll say that yeah, okay, let me continue with this and then I'll give the definition later on. So, and here I have phi alpha, phi beta. And as usual, we are concerned with the red region, which is where the transition function is defined. So phi beta. So here I'm doing phi beta composed with phi alpha inverse. We'll take the green region to the red region, and I'm looking at the derivative of that and the determinant of the derivative. Well, what I can do is I can pull back the form. Omega is on the whole manifold, so I can pull it back to get phi upper star omega here, and here I get phi beta star omega. Now, these are n forms on open subsets of Rn, possibly different open subsets, the green part and the blue part. At any rate, they are open subsets of Rn and these are n forms. So, therefore, I can write phi alpha star omega at every point in the green portion. It will be, we know that the space of n forms is one dimensional for a vector space. So if I take any point, this form will be a scalar multiple of the standard form dx1 wedge dxn. But as usual, the scalar multiple will change from point to point. So I can write it as a function times dx1 dxn. So this f is a function on C infinity of this green part. I'll just write green open set and phi beta star omega will be another function times dx1 dxn, where G is C infinity of the blue open set. Now what I'll do is I'll just say that I look at, suppose we define an oriented atlas by it's a collection of all charts U alpha, phi alpha, such that when I pull back this omega, I'll get this thing here with f is strictly positive. So it's this function, in any case it's a non-zero function because this omega is a non-zero form and this phi alpha star is an isomorphism of the alternating mappings. So this is a non-zero form, so therefore this f has to be non-zero. So I want it to be, I look for those for which it's just positive. Now this gives a system of charts on M. It's not clear yet that I can even get an atlas, and the other thing is, for this, why is it the case that the transition functions have the required property? So let's just check the transition functions. transition functions condition, that's just a matter of relating this f and g. So notice that well, phi alpha inverse this map, the transition function map, I can use this upper star to pull back this form to this form, to pull back this form here, and not surprisingly the pullback of this will give me this, because anyway the whole thing was obtained just from omega. So it's not surprised that this is equal to, you can directly do the calculation here in fact. So phi alpha inverse and then phi beta upper star, oh oops, sorry, here actually I should be a bit careful. It's not the, I should use phi alpha inverse rather than phi beta, so inverse. So here everywhere I should change it a bit. So phi alpha inverse star, phi alpha inverse star, and here too phi alpha inverse star, phi alpha inverse star, and here it would be star, and here too this. Because yeah, I would need to go back to this, and then phi alpha inverse star will give me something here and so on. Well, if I do this calculation, this phi beta inverse star will cancel, the order will get reversed after I take star, and then it's easy to check that I'll just get phi alpha inverse star of omega. So in other words, this diffeomorphism between you, the point is that now this equation, everything, all the objects are defined on Euclidean space. And but we know that whenever we have a diffeomorphism between two open sets, and if you have an n form here, actually it's a vector space statement, but it translates to this f star. So here omega is here, f star omega, and I don't even need diffeomorphisms for this. I just need u and v to be open sets in Rn. So omega f star omega equal to determinant of df times omega. This is valid only for n forms. So we have something like this, and this again can be reduced to a vector space statement. We have proved that whenever you have a linear transformation from V to V and omega is an n form, T star omega is determinant of T times omega. It's the same thing here, which I'm using here. So in short, the determinant, and here the map is, the f here is this map. Therefore, determinant of derivative of this transition function is, well, now what we note is that this the left hand side on the other hand is phi beta composed with phi alpha inverse star. Now this thing is what we called G omega, and this is what we called F omega. And this, as usual, when I do this, it becomes the pullback of this function, which is G composed with phi beta composed with phi alpha inverse multiplied by G star omega. And the right hand side is F omega here, and the no, sorry, not that. This, it's not omega here, it is the standard form. Let me give it a name instead of writing it every time. So here omega naught is dx1 dxn. So I've just written this in terms of g omega naught. So here let me just end with this calculation, and then the pullback of right. So where was I? Yeah, fine. So this equal to this, and right. So this is times phi beta phi alpha inverse star omega naught is what I get here. So let me so ultimately, and what we have to observe is that, and this again, this thing is determinant of d of phi beta composed with phi alpha inverse times omega naught. So the left hand side will be the product of this, and the right hand side is just f. But since we have assumed both f and g are positive for my atlas, it will force this determinant also to be positive. So therefore I get an oriented atlas. So I'll stop here. In the last lecture I'll make a few more remarks about this, and then we'll end there. Okay, thank you.